Welcome to Math 1300, Nunez Community College. This is section 5.6, which is exponential and logarithm equations. In order to solve exponential equations, which is the first thing we're going to look at, we try our best to write the bases the same. If we can write the bases the same, then the exponential functions are equal to each other, which then would make the exponents the same. Example, if I have 2 to the 3x minus 9 equals 16, it's actually minus 8, equals 16, I'm looking at this and 2 is a prime number, 16 is not. Can I write 16 with a base of 2? And yes, we can. This will be 2 to the 3x minus 8 equals 2 to the 4th power, because 2 times 2 times 2 times 2 is 16. So 2 to the 4th power. If we can accomplish writing both bases with using the same number, and the total quantity is equal to the total quantity, then we can say that the exponent is equal to the exponent. So we'll take the exponent out and do 3x minus 8 equals 4. We can then solve for x, bringing the 8 to the other side, 3x equals 12, and dividing by 3, we'll get x equals 4. So the first step in trying to solve an exponential equation, because it's exponents, and the exponent is the variable, we're going to try to solve it by writing the bases the same. Suppose we have 27 to the x plus 3 equals 9 to the x minus 1. 9 to the x minus 1. In this case, we cannot In this case, we cannot write 27 with a base of 9. However, we can write 27 and 9 with a base of 3. So 27 will be 3 to the 3rd power raised to the x plus 3, and 9 will be 3 to the 2nd power raised to the x minus 1. Now, when we have a power raised to a power, we multiply. So this is going to be 3 to the 3x plus 9, because the 3 has to be distributed to both, equals 3 to the 2x minus 2, because the 2 has to be distributed to both. Now we've accomplished our goal of writing the bases the same, so we can use that same technique and say that the exponents must be equal to each other. And now we solve, bring the 2 across, x plus 9 equals negative 2, bring the 9 to the other side, and x equals negative 11. So that's the technique that we're going to use. We're going to try to write the bases the same. Try to write the bases the same. Now, if we look at it and we cannot write the bases the same, we have to use another technique. The technique we're going to use is what we learned in a previous section called the power rule. In order to use the power rule, what do we have to do? We have to take the logarithm. The logarithm will allow us to bring the power out front. So if I have 4 to the power of x equals 15, I cannot write a 4 and a 15 using the same base. So I'm going to take the log of both of them. As long as I take the log of both of them, I can use the power rule and bring the exponent out front. I personally like using natural logs rather than regular logs. So in each of these, I'm going to write the natural log. So it's the natural log of 4 to the x equals the natural log of 15. From here, I bring the x out front. I got x natural log of 4 equals natural log of 15. And now to solve for x, I'm going to divide by natural log of 4 on both sides, giving me that x is equal to natural log of 15 over natural log of 4. Now, if they ask for the exact value, then this is the exact value. However, if they ask for an approximation, we punch in natural log of 15 divided by natural log of 4, and we come up with x is approximately, in this case, 1.95. Again, it depends on what they ask. They may ask you to do an approximation and bring it out 2, 3, or even 4 points, decimal points, or they may ask for the exact answer. This is the exact answer. The other one is the approximation. Okay? From here, literally the only thing we change is the algebra. The algebra gets a little more tricky. The algebra has a couple more things to do, but it basically goes back to things that we learned back in high school, in our old high school days. So we have 40e to the 0.6x minus 3 equals 237. Now initially it looks like there's a lot to do, but it's really not. It's almost like if we had 40x minus 3 equals 237. If this was our problem, we would solve for x by bringing the 3 to the other side. 40x equals 240, and then divide by 40, and x would equal 6. Well, it's the same thing, except instead of x equals 6, it's e to the 0.6x. So I'm going to have 40e to the 0.6x equals 240 by bringing the 3 over, because I want to isolate this so that I can take the natural log of it. Then I'm going to divide by 40, and e to the 0.6x equals 6. Now that I've isolated it, I can take the natural log. Natural log of e to the 0.6x equals natural log of 6. And now the power rule brings this out front. 0.6x natural log of e equals natural log of 6. Now, natural log is the one I like to use, and the natural log is the one we have to use in this case, because the natural log of e is one of the general log properties that we learned. The natural log of e is 1. So I don't have to write anything, it's 1. And then we solve by dividing by 0.6x, so natural log of 6 over 0.6. This is the exact value. If I do the approximation comes up to be approximately 2.99. 2.99. Again, depending on which one Cengage is asking you to put the answer in. Okay, moving on for the next example, it's just a matter of being able to maneuver through the algebra, and we're going to come up with the same thing. Suppose I have 5 to the x minus 2 equals 4 to the 2x plus 3. 4 to the 2x plus 3. In this case, we're going to, again, take the natural log of both so I can use the power rule and bring them out front. So natural log of 5 to the x minus 2 equals natural log of 4 to the 2x plus 3. When I bring them out front, I have x minus 2 times natural log of 5 equals 2x plus 3 times natural log of 4. Now the natural log of 5 has to distribute to this binomial, and the natural log of 4 has to distribute to this one. So that'll give me x natural log of 5 minus 2 natural log of 5 equals 2x natural log of 4 plus 3 natural log of 4. Now my goal here is to solve for x, and I have an x, which is this thing on the left, and I have an x, which is this thing on the right. So I'm going to bring both x's together. I'm going to bring the 2x natural log of 4 to the left, and in the meantime, this has no x, so I'm going to bring this to the right. So I'm going to add 2 natural log of 5 and subtract 2x natural log of 4. That'll give me x natural log of 5 minus 2x natural log of 4 equals 2 natural log of 5 plus 3 natural log of 4. The reason I wanted the x on one side is because now both of them have an x in it. I can factor an x out. So I factor an x out and I'm left with natural log of 5 minus 2 natural log of 4 equals 2 natural log of 5 plus 3 natural log of 4. And now I can divide by this, because that's what I don't want. Divide by natural log of 5 minus 2 natural log of 4 on both sides. And that's what I get as my answer. X equals 2 natural log of 5 plus 3 natural log of 4 over natural log of 5 minus 2 natural log of 4. This is again the exact answer. If you put it all into the calculator and you get an approximation, it comes up to negative 6.34. Negative 6.34. That's about the extent that we're going to go into with solving exponential equations. Solving exponential equations. Now we're going to look at solving equations that are in log form. Now remember, to solve an exponential equation, we did the log of both sides. So to solve a log, most of the time we're going to look at turning it into an exponent. So example 5 says log base 4 of x plus 3 equals 2. And I'm going to take this and I'm going to rearrange it as an exponent, and it makes a lot more sense. This is what? The base is 4 to the second power equals x plus 3. And now we just do the operations. 16 equals x plus 3. X equals 13. That would be our answer. So change the log to an exponent and then do your operations in order to solve. Suppose we have an operation like 3 natural log of 2x equals 12. 3 natural log of 2x equals 12. Well, it is a log. It's a natural log. And what did I say? Well, I said turn it into an exponent in order to solve it. Well, the first thing I want to do is I want to isolate it. This is 3 times that. So I'm going to divide both sides by 3. And I get natural log of 2x equals 12 divided by 3, which is 4. Now, I know this is natural log, but it still doesn't look quite like I'm used to seeing it. So I'm going to write natural log as what it is. What it is log base e. That is natural log. Log base e of 2x equals 4. And now I can turn this into an exponent quite easy. It's e to the 4th equals 2x. And therefore, I now what? Divide by 2. And x equals e to the 4th over 2. X equals e to the 4th over 2. And finally, what happens if we have one that we have to do one of the rules for, as in the product quotient power rules? Suppose I have log base 2 of x plus log base 2 of x plus 7 of x minus 7, x minus 7 equals 3. In this thing here, I want to be able to rewrite it as an exponent. But in order to rewrite it as an exponent, I have to use the rule where when I'm adding them, that's the product rule, to put them together as a single log. So this is going to be log base 2 of x times x minus 7 equals 3. Now we do have a single log. I can rearrange it as an exponent. It'll be 2 to the third power equals x times x minus 7. Now in order to solve this, since I now have this, I'm going to what? Distribute the x and do 2 to the third power. That gives me 8 equals x squared minus 7x. When we have something that is squared, that is quadratic, so we zero rule it and then we factor. So I have x squared minus 7x minus 8 equals 0. And when we factor this, this comes up to what? X and x. 8 to give me 7 would be 8 and 1. And it's got to be a negative 7, so that's a negative and that's a positive. Again, with the insides and the outsides, that's 1x, negative 8x to give me negative 7x. So now, either this one's 0 or that one's 0 in order to equal 0. So x plus 1 equals 0, or x minus 8 equals 0, x equals negative 1, or x equals positive 8. That is my 2 answers on that one. And everything's looking great, except for the fact that when we have this, we need to go back in and plug the answer in to make sure. Go back in and plug the answer in to make sure it's okay. And negative 1 going here or here gives me a negative. And if we go back and remember what the log says, remember the log equation looks like this, and the domain of a log equation is from what? Domain is from 0 to infinity, not including 0. The domain can never include 0 or negative numbers. So if we have a negative domain, that number's out. 8 on the other hand is good here, 8 on the other hand is good here. So 8 is the number that we would use. And that checks off for that particular problem. Okay, well, this here concludes section 5.6. I will see you at the next one.